We're asked to find and describe the domain of a function g of x, y, z that is given by x cubed y squared z times the square root of 10 minus x minus y minus z. Since we have a square root in this function, what we need is that 10 minus x minus y minus z, the radicand, is greater than or equal to 0, which means that x plus y plus z must be less than or equal to 10. And that in fact gives us our domain. Our domain is the set of ordered triples x, y, z such that x plus y plus z is less than or equal to 10. As far as describing it, x plus y plus z equals 10 is a plane. We can represent the portion of the plane in the first octant by considering intercepts. The x, y, and z intercepts all have a value of 10, and so we see this triangular portion of the plane in the first octant. The idea, though, is that x plus y plus z is supposed to be less than or equal to 10, and so the sum of x, y, and z being less than or equal to 10 means we're looking at points that are below this plane, and that's the description. We should define the space that we are in, points in R3. On or below. I don't think I said on before, but it's less than or equal to, so on or below the plane x plus y plus z is equal to 10. And that's our description of the domain. Next, we're going to find and sketch a domain. Our function is f of xy is equal to the fourth root of x minus 3y. So we see that we have a two-dimensional input. Our sketch is going to be on the xy plane. First, though, we're going to find the domain, and because we have a fourth root, that's a radical with an even index, we know that the radicand, x minus 3y, has to be greater than or equal to 0. If you want to express this using fewer symbols, you might say that x is greater than or equal to 3y by adding 3y to both sides. And then, folks, what I'll tend to do is just wrap set notation around what we've just written. So the set of ordered pairs xy such that, what we already wrote, x is greater than or equal to 3y, close the curly braces, and that gives us our domain. However, we were also asked to sketch it. Again, f of xy being the function means that our domain exists in the xy plane. And another way to consider the line x equals 3y is that it is y equals 1/3 x. So we're looking at a line through the origin that has a slope of 1/3. The associated inequality is actually y is less than or equal to 1/3 x, and so we're looking at values that are below this line. So shading below that line represents the domain. Next up, same instructions, new function. G of xy is equal to the natural log of the quantity of 2 minus x divided by 1 minus x squared minus y squared. Looking at the denominator, we see that x squared plus y squared cannot equal 1. So that excludes the unit circle. Looking at the numerator, since we have a natural log of 2 minus x, we know that the natural log function has a domain of positive values. And so 2 minus x has to be greater than 0, or x has to be less than 2. We need to incorporate both of these. So we'll say that the domain is the set of ordered pairs xy such that x is less than 2, comma, x squared plus y squared does not equal 1. So there's the find the domain portion, but then we're asked to sketch the domain as well. Because our g is a function of x and y, we again have a domain that is represented on the xy plane. We need to exclude the unit circle, and so a circle of radius 1 centered at the origin. I redrew it because I didn't like the first iteration. But also we're looking at that x is less than 2. So I'm going to draw a vertical line where x is equal to 2. It's a dashed line. I'll mark here that we have the circle of radius 1, so I'm just putting marks on the x and y axes there. And the domain is all of the numbers that are less than, well, all the x values less than 2, so shading to the left of the vertical line. But also inside of the unit circle, the only thing we're really excluding after we've gone to the left of 2 is the unit circle itself. And you may be wondering, what on earth can this graph possibly look like? Well, I've graphed it using the GeoGebra 3D graphing tool. And what you can see here is the XY plane. We're looking straight down at it. We see that we have a vertical line here at x equals 2, and the function exists to the left of that. And then there's this nice circle here of no function here at the unit circle. But that is just the domain. As far as the function itself, here you go. It's in pieces, as you can see.